Hello friends, welcome back to this online certification course on watershed hydrology. I am Rajendra Singh, professor in the Department of Agriculture and Food Engineering at Indian Institute of Technology, Kharagpur. We are in module 4, this is lecture number 2 and the topic is estimation of runoff. In this particular lecture, we will be covering estimation of runoff by estimating losses, runoff calculation by infiltration method, estimation of peak rate of runoff by Cook's method, and just to have a recap of what we discussed when in the previous lecture we started the methods of runoff estimation, and there I gave you the list of methods, and in the previous lecture we discussed empirical formula and tables. For example, if you remember, we discussed Binny's percentage for Madhya Pradesh, Barlow's table for Uttar Pradesh, and English and decision formula for Maharashtra. And today's lecture already we have seen that we will be discussing about these three methods, and rest of the methods we will take in future lectures. Now, coming to runoff calculation by estimating losses, we have a couple of formulas here. The first formula is A.N. Khosla formula, which came into existence in 1960, and basically as per Khosla's formula, monthly runoff RM, so in millimeters. So basically it works on the monthly time scale, that is very important to remember, and so runoff in millimeters is calculated using the monthly precipitation PM and monthly losses LM all in millimeters. So, it gives a runoff in millimeters, and these two equations are used, that is RM is equal to PM minus LM, that means runoff is precipitation minus losses, where for estimating losses we have to use this relationship, that is where 5 LM equal to 5 TM, where TM is the mean monthly temperature of the basin in degree Celsius. And this relationship, equation number 6, we remembered we are continuing with the equations in the previous lecture, because we are still discussing about estimation of runoff losses, though we have broken into lectures, but basically it is the topic remains the same, that is why we are continuing with the equation numbers from the previous lecture. So, as I was telling that for using equation number 6, there is a condition that this equation could be used only if temperature, the mean monthly temperature of the catchment is greater than 4.5 degrees. So, all instances where temperature is greater than 4.5 degrees, loss can be estimated by multiplying the temperature by 5 times, and then of course, the runoff can come after deducting the losses from the precipitation value, and monthly M remains M suffix shows monthly time scale. What happens when temperature is less than 4.5 degree or equal to 4.5 degree? If that is the case, then Khosla provided a table where it directly gives us the loss values. So, if temperature, say for example, is 4.5 degrees, then LM value is 21 millimeters. So, that means that as soon as PM is greater than 21 mm, if the temperature at 4.5 degrees C, if the temperature is 4.5 degree, then we will get runoff. As long as rainfall is below 21 millimeters, we will not get any runoff. Similarly, if the temperature goes into minus, that is minus 18, say for example, then the loss reduces to 10 millimeters. So, in Khosla formula, monthly time step where LM, that is losses, are related to or associated with mean monthly temperature. If depending upon whether temperature is greater than 4.5 degrees C or equal to or less than 4.5 C, we can use equation or the directly table, and then RM equal to PM minus LM can be used for estimating the runoff loss. The second equation is given by David Lloyd's. So, it is known as the David Lloyd's formula, and it came into being in 1938. And as per this formula, annual loss. So, obviously, this is annual time scale and it gives relationship for loss itself. In the previous case, we saw that we got a relationship for loss, but then we had also equation number 5. So, equation number 5 at annual time step remains valid for this method also. Only thing is that instead of equation number 6 which was there for Khosla method, we will be using equation number 7. So, annual loss L in centimeters can be estimated from the following relationship, which involves annual precipitation, annual temperature, annual duration of sunshine hours and losses due to percolation. So, this is the relationship given by equation number 7, where L is 0.644 p to the power 0.87 plus 0.569 t minus 16 plus 0.0152 s minus 1450 plus g, and P is the annual rainfall over the area in centimeters, T is the mean annual temperature in degree C, S is the annual duration of sunshine hours over the area in hours. So, obviously, knowing the latitude and longitude, you can find out the value of S, and L is the annual losses which we are calculating here in centimeters, and G is the losses due to percolation in centimeters. So, that means if we know the know the temperature, annual duration of sunshine hours and losses due to percolation and also precipitation, we can estimate a loss. And of course, once we know the loss, then obviously as I already mentioned that runoff will be nothing but precipitation minus loss. So, using this relationship, we can find out how much runoff has, what amount of runoff has occurred in the basin. So, pretty straightforward methods of calculating runoff. Let us take an example. For the Kangsavati river basin, the mean monthly rainfall and temperature are tabulated below. The river basin has a drainage area of 6,488 square kilometers. So, for different months of a year, January to December, we have been given temperature in degree C and rainfall value in millimeters. So, in January, the temperature is 20 degrees and rainfall is 105, wherein in the month of July, temperature is 39 and rainfall is highest at 1210. We have to estimate the total annual runoff volume for this basin using Khosla's formula. So, we have to use Khosla's formula, and since the monthly time step data are given, that equation the equations which are meant for monthly estimation, they fits well. So, as per Khosla's method, RM is PM minus LM, that we know, where monthly runoff is monthly precipitation minus monthly losses. Thus, for different months, losses are first calculated using LM equal to 5 Tm for Tm greater than 4.5, and then they are deducted from the rainfall to determine the runoff. So, Kangsavati is in West Bengal. So, obviously, we always expect that temperature will be greater than 4.5 degree, which is also evident from this table. The temperature was the lowest temperature was 20 degree. That means all the time temperature are greater than 4.5 degrees. So, we can straight away use this relationship LM equals to 5 Tm, which was given by question number 6 in the previous slide when we were discussing the method. So, obviously, we know for each month we know temperature, we know rainfall, and then obviously losses are nothing but 5 times of temperature. So, for January it is 100, for March 34 times 5 which is 170, for July it is 39 times 5 is 195, and for December it is 22 times 5, that is 110. And obviously, then runoff is nothing but rainfall minus losses. So, these two rows will be used. So, runoff value comes out to be 5 in January and so on for each month. And the total runoff we get is in depth units we get is 6,430 millimeters. So, that is the total runoff we get, and because we have to get the runoff volume. So, total runoff volume will be nothing but if we multiply this runoff depth by basin area, we will get the runoff volume. So, it is sum of RM which is 6430 and area which is area which is already given. So, only thing is that we are manipulating the units here, like here this 6433 is in millimeters. So, we are putting here 64330 times 10 to the power 5 in meters, 10 to the power 3 in meters. Similarly, our basin area is given as 6488 square kilometers. So, we are putting that in square meters, that is 6488 into 10 to the power 6 square meters. And then obviously, because we would get a huge number, so we are dividing everything by 10 to the power 6 to get the final answer in million cubic meter, and our final answer comes out to be 41,717.84 million cubic meter. So, using A&Khosla method for the basin, the total runoff volume we get is 41,717.84 million cubic meters. Then we come to the next method, that is runoff calculation by infiltration method. And as we have already discussed while discussing the infiltration, we have discussed that runoff can be determined using infiltration indices like phi index or W index. And if you remember, we said that basically these phi index or W index, that is infiltration indices, they are nothing but they represent the average loss. They represent the average loss over the basin. And if you remember, we said that we use hydrograph in this case, that is rainfall intensity versus time plot, and these are the hydrographs representing the rain. And then obviously we draw a phi index line. If we know the phi index, we draw the phi index line, and volume of runoff, the area under the curve, area under the curve, that is rainfall hydrograph, gives us the runoff volume. So, that means area under the curve of hydrograph if we get, then we get the runoff volume. And below that, basically if you recall, we said that initially there will be initial abstraction, and then obviously there will be infiltration continued even after runoff initiation. So, IA is the abstraction losses including infiltration before the runoff began, and F basically represents the infiltration after runoff has occurred. And since infiltration indices represent the average infiltration losses over the basin, the method is not 100% accurate, but gives satisfactory result. I think this point also we discussed earlier, because of the simple reason that we know that say infiltration or other abstraction, these keep on changing from one point to the next, especially infiltration with soil characteristics changing, infiltration keeps on changing within a basin. So, it may be very difficult to take the actual values of infiltration in estimating losses and then runoff, and that is why the concept of this average loss or average infiltration indices, that is phi index or W index, has been taken into consideration, or they have been used. Let us take a simple example. The observed rainfall of a 12-hour duration is given in the table below. If the phi index of the storm is 5.2 millimeter per hour, determine the total runoff. So, for different duration, that is 0 to 12 hours, a 2 hourly time step, we have been given cumulative rainfall in millimeters. So, obviously, this is what is given at different times. We have been given cumulative rainfall, that is at 0 time it is 0, and then at 2 hours it is 5.6, at 4 hours it is 25.6, and so on. So, first thing what we will do is that we will prepare a table, the first column showing rainfall during the 2 hour interval. It is 2 hourly, so that is why we are using 2 hour interval in millimeters. So, obviously, the first 2 hours, 0 hour nothing. So, first 2 hours, at 2 hours the rainfall will be 5.6 minus 0 is 5.6 mm. In between 2 to 4 hours it is 25.6 minus 5.6, that means 20. Next 54.4 minus 25.6, that is 28.8. 62.4 minus 54.4, 8. Then 68.6 minus 62.4, 6.2. And lastly 110 minus 68.6, that is 41.4. So, this is the rainfall during the 2 hour interval. And then obviously, we can find out the intensity of rainfall at these 2 hourly interval, and of course, this is 2 hours. So, divided by 2 we will get the value in millimeter per hour. So, the intensity comes out to be 2.8 in first 2 hour, and then last 2 hours it is 20.7 millimeters per hour. We have been already given the value of phi index and which remains constant throughout. So, this is given as 5.2 millimeters per hour. Now, we have to find out the direct runoff. So, remember that we previous graph also we said that this is just a typical hydrograph if we plot, and if you plot the phi index value, then direct runoff is only contributed by the hydrograph slices, which are the bars which lie above the phi index value. So, because in this case the intensity of rainfall is lower than the phi index, that means there will be no runoff produced here, and same concept is used, and remainder of that 10 minus 5.2 is 4.8, 14.4 minus 5.2 is 9.2, and in these two also it is less than in phi index. So, that means there will be no runoff generated, and the last slide it is 20.7 minus 5.2, 15.5 millimeter per hour of rainfall which generated. Now, because we want the direct runoff depth, so obviously we have to multiply it by 2 again to get the direct runoff, and that is why we are doing. So, 0, 9.6, 18.4, 0, 0, 31. So, total runoff depth that has been obtained here is 59 millimeters. Thus, the runoff during the event is 59 millimeters. That comes from the calculations here. So, this is a simple procedure. Only thing you have to remember that only when the intensity is greater than phi index, only in those duration runoff will be generated. Then we come to the Cook's method of estimating peak rate of runoff, and this method was developed by USDA, that is US Soil Conservation Service 1953, that is United States Department of Agriculture, and the runoff characteristics of a watershed in this method are carried under 4 categories or evaluated, that is relief, soil infiltration, vegetation cover and surface depression, and numerical values are assigned to each runoff characteristics, and for that SCS has provided this table. So, here these are conditions, that is relief, soil infiltration, vegetation cover and surface storage, and on this side we have 4 columns which basically represent the combined effect of these 4 characteristics: relief, soil infiltration, vegetation cover and surface depression. So, obviously when we have extreme peak column where some of these values comes out to be 100, that means the conditions, all conditions that is be it relief, infiltration, vegetation cover and surface depression are in favoring runoff generation. So, for example, relief is when it is a steep and rugged slope greater than 30%, that means all the water will flow because of the very steep slope of greater than 30%. So, we gave a score of 40. Soil infiltration, no effective soil with negligible infiltration. So, there is no infiltration, that means entire precipitation will get converted into runoff. So, that is why we give a value of 20. Then vegetation cover, no effective cover, that means again there is no absorption. So, most of the rainfall will get converted into runoff. So, that means again we have a highest value of 20 in this category. And surface storage, negligible ponds or marshes, that means there is no surface storage, then again max value of 20, and that is why if you sum all these 4 values 40 plus 20 plus 20 plus 20, that value comes out to be 100. So, that simply means that almost all the precipitation will get converted into runoff. On the other extreme, we have low peaks where the sum value is only 25. Under relief, it is flat land slopes lying between 0 to 5%. So, we give a score of 10, that is 25% of what we gave under extreme peaks. Soil infiltration, deep sand takes up water rapidly, that means infiltration rate is very high. So, of course, 1/4 here again 5. Vegetation cover, good to excellent cover, 90% grass. So, that means lot of absorption. So, again we give 1/4 5. And surface storage, high surface depression storage, that means most of the water could be stored in the depressions. So, that is why again 1/4 of the value. So, that is why sum of these will be 25. So, these values first come from this table. Now, the steps are that evaluate watershed characteristics based on the relief, soil infiltration, vegetation cover and surface depression, and assign the numerical values from this table. That is all the basin characteristics, you assign the numerical values using the table wherever they fit, and find the sum of numerical values assigned to the characteristics, that is which is called W, that is sum of R, I, V and D, that is for all 4 characteristics sum. We saw that it could be max 100 and minimum it could be 25. Then determine the uncorrected peak runoff rate P from the runoff curve based on W and watershed area. So, basically SCS or USDA has provided a ready-made curve where peak runoff in cubic meter per second is related to watershed area in hectares, and there are, you can see that there are different curves for different W values. W, you remember, is sum of the numerical values assigned to these 4 characteristics. So, depending upon whether W is 30, 40, 50, 60 or 80, these curves can be used. So, what happens that if you use this curve, then if you know the watershed area, W value we already know. So, we will find out the discharge from here. Say for example, if the watershed area is around 8 hectares and W is equal to 80, then we will get the peak discharge here, which is referred to as uncorrected peak runoff rate P in Cook's method. Now, we compute the adjusted runoff rate for the desired recurrence level and watershed location using this relationship, which is the main Cook's method equation, QP equals to PRFS, where P we have already estimated, which is the uncorrected runoff peak. And QP is peak rate for a specified geographical location and recurrence interval cubic meter per second. P is the uncorrected peak runoff rate. We have already seen how to determine that. R is geographical rainfall factor, which is different for different region, basically depends on latitude and longitude. Frequency factor, F is frequency factor and S is shape factor. Now, frequency factor for different zones of India are already developed, that is for zone 1, 2, 3 and 4, and for different recurrence period frequency factor values can be read from this table. Similarly, shape factor for different sizes of earthwork, where basically length and width ratio is linked to the watershed area for different areas, and for different length and width ratios we have values of S. So, F and S we can read from here, P we have already got, R will get knowing the location, the geographical rainfall factor, and thus we can obtain the PRFS. Using the PRFS we can get the Cook's method example. Now, let us take an example. A 20 hectare watershed has an average slope of 5 to 10% and its width ratio is 3. It has deep loam soil with good infiltration characteristics and grass cover is fair. The watershed has a moderate amount of lakes and ponds, which is less than 20% of the depression storage. The watershed belongs to zone 3. The geographic rainfall factor of the area is 1.2. Find the peak rate of runoff for a return period of 25 years. So, it is a simple application of Cook's method. So, we have been given watershed area is 20 and different watershed characteristics are given here. So, rain relief factor is average slope of 5 to 10%. Soil infiltration characteristics, deep loam soil with good infiltration characteristics, vegetation cover, fair grass cover, surface storage, moderate amount of lakes and ponds, less than 20% of depression storage. So, that means knowing all these characteristics, we can enter and read the values from the table for obtaining the value of W. So, here as per our given description, R is 20, soil is 10, vegetation cover is 10 and less than 20% depression storage, remember surface storage is 10. So, that means the numerical value, sum of numerical value W we obtained for this watershed is 50. So, now knowing the watershed area of 20 hectares and the W value of 50 which we have obtained, using the curve we can get the uncorrected peak runoff rate from this curve. So, here W equals to 50, watershed area is 20. So, the value of P we get is 1.9 cubic meter per second. So, the uncorrected peak runoff rate is 1.9 cubic meters per second. Now, the geographical rainfall factor for this area is already given 1.2, and watershed falls under zone 3 and return period is 25 years. So, obviously, we have to use this table zone 3 and return period is 25 years. So, value of frequency factor is 1.3. So, the value of F is 1.3. Similarly, length to width ratio of the watershed is given as 3, area of the watershed is 20, and the shape of factor of the watershed can be read from table, that is, this is length to width ratio, watershed area is 20. So, we get a value of S factor of 0.81. So, now we know all 4 values. So, QP is PRFS 1.9, 1.2, 1.3 and 0.81, and thus the peak rate of runoff comes out to be 2.4 cubic meter per second. So, the peak rate of runoff for the watershed is 2.4 cubic meter per second as per Cook's method. We will take another example. A watershed having an area of 40 hectares has a hilly land slope of 10 to 30%. Its length to width ratio is 4. The soil in the watershed has a poor natural cover and low infiltration characteristics. This watershed has no superficial depression. The watershed comes under zone 4 and geographical rainfall factor for the area is 1.25. Find the peak runoff rate for the watershed with a return period of 50 years. What will be the change in the peak rate of runoff if excellent vegetation cover is developed in the watershed? So, that means we have to first find the value and also the change if vegetation cover changes to excellent. So, we have been given area of the watershed is 40 hectares, relief characteristics, hilly land slope 10 to 30%, soil infiltration characteristics, low infiltration characteristics, vegetation cover poor, surface storage, no superficial depression. So, knowing this, we can get the values from here to 10 to 30% is 30 R. Similarly, low infiltration characteristics 15, poor natural cover we get V equals to 15, and also surface storage no parts, no superficial depression we get D equals to 20, which is here. No, not here, but here. Negligible ponds or marshes. So, that means 20. So, the sum of numerical values we get W equals to 80 from the table. Now, knowing W equals to 80 and watershed area is 40, we can get the uncorrected peak runoff rate, which comes out to be 13 cubic meter per second. Now, geographical rainfall factor for area is 1.25, which is already given, and watershed belongs to zone 4. Return period is 50 years, zone 4, 50 years, the value comes out to be 1.3. Similarly, length to width ratio of the watershed is given as 4. Total area already we know is 40 hectares. So, for 40 hectares and length to width is 4, the value of shape factor is 0.72. So, we read that. So, now we know that Q1P, that is under given condition PRFS, if you put, the value comes out to be, QP value comes out to be 15.21 cubic meter per second. But we also have a condition that if the vegetation cover, what happens if the vegetation cover changes to excellent. So, for excellent cover, the V factor, you can see here, it will change to 5 as per table. So, that means our W value will reduce to 70, earlier it was 80. So, that is the change we are getting, and that means for 70, W equals to 70, area equals to 40, we get uncorrected value of 9.5 cubic meter per second from graph. All other things remain the same, that means R, F and S remain the same because no changes are taking place. So, obviously, we get a discharge of 11.12 cubic meter per second. So, obviously, there is a reduction in discharge. So, the decrease in runoff, peak rate of runoff Q1P minus Q2P by Q1P, and of course, percentage, that is why we are multiplying by 100. So, that value we get is 26.89%. So, it shows that there will be a decrease of 26.89% in the peak runoff rate if the vegetative cover changes from poor to excellent. So, that is how we saw that we can use Cook's method to find out provided the data. Of course, the data requirement is pretty huge, but if you know all the characteristics, then you can use Cook's method for estimating the peak runoff rate. So, in this lecture we saw the runoff estimation using losses, using infiltration estimation, and also using Cook's method. Thank you very much. Please give your feedback and also raise your doubts and questions on the forum, which we will be happy to answer. Thank you very much.